My dear students, today we are going to discuss on the topic resonance effect and its applications. We have already gone through the topic resonance effect, detailed explanation, and the mesomeric effect also. I'll give the link for the same class in description. And here we are going to discuss its applications. The first application is the low reactivity of vinyl and aryl halides when we compare with alkyl halides on nucleophilic substitution reaction. As you all know that a nucleophile, what is a nucleophile? A nucleophile is a substituent or a species which is having lone pair of electrons or rich in electron rich species. So which needs a positive center to attack. So consider this example. This is an alkyl halide. X is halide group. This is R is a alkyl, aliphatic alkyl group. When a nucleophile is having lone pair of electrons and a negative charge, when a nucleophile attacks this group, the more electronegative halide group will pull the electron from the shared pair of electron towards itself. As a result of that, a partial positive charge on alkyl group and partial negative charge on the halide. And when the nucleophile attack prominent there, a carbocation will form along with a halide is formed. This nucleophile then attack this carbocation, forming a nucleophilic substituted product and halide ion. Right? This is the normal nucleophilic substitution reaction on an alkyl halides. But what is the application of resonance on it? Low reactivity of vinyl halides. What is a vinyl group? CH2 double bond CH and vinyl halide, a halogen is attached to it. This is called vinyl group and halide is attached to it. Halide is having lone pair of electrons, right? So a lone pair in alternative to pi bond, that is a conjugate system, resonance is possible. So what will going to happen? This lone pair will comes here and this will goes to the terminal current. As a result of that, CH2 minus CH double bond X plus, right? Again, this will comes to here and this will goes to here. CH2 double bond CH and X minus. So we can write the hybrid structure as CH2 single bond CH X minus and plus. So we can see that through resonance there is a partial double bond character between carbon and halogen atom, right? So when a nucleophile attack this vinyl halide, it will get the attack, the substitution will hinder due to the presence of a partial double bond character between carbon and halogen group. So which will decreases the possibility of having nucleophilic substitution reaction, right? So the nucleophilic substitution reaction on vinyl halide is decreased due to the presence of a partial double bond character between carbon and halogen atom through resonance phenomenon. Okay. Similarly, when we consider an aryl halide, see this is a benzyl chloride, a chlorobenzene. So benzene, there is a lone pair of electrons. What will going to happen according to plus R effect? When a lone pair is carried by a functional group, the electron will move towards itself and a delocalization of negative charge happen inside the benzene ring. So as a result of that, negative charge here, a double bond character between here. This negative charge comes to here, this goes to here. This negative charge comes here, Cl plus. This negative charge comes here, this goes to here. This negative charge comes here, this will come here. So finally the compound will become Cl. The hybrid structure will become a partial double bond character. A partial double bond character between Cl and N. So we can see that just like a vinyl halide, we can see that there's a partial double bond character between carbon and chlorine atom, right? When a nucleophile when a nucleophile approaches to this group, this aryl halide or chlorobenzene, due to this partial double bond character between carbon and chlorine atom, the displacement of chlorine from the aryl group is very difficult. In addition to that, one more point. Due to plus R effect of this substituent chlorine atom, the electron density on the benzene ring will increases, which will hinder nucleophilic substitution reaction because nucleophile itself is an electron rich species. So the negative charge delocalization will hinder the approach of nucleophile. So these are the two reasons why aryl halide is less reactive towards nucleophilic substitution when compared with the alkyl halides. Okay. Now we move on to the second application, that the high reactivity of allyl and benzyl halides than alkyl halides towards nucleophilic substitution reaction. We already discussed that when a nucleophile approaches to an alkyl halide, this will goes to here and nucleophile attack the carbocation. The carbocation form plus and a halide ion. And what about this allyl group? Allyl group is nothing but CH2 double bond CH single bond CH2 and a halide group is there, right? Halide group is having lone pair of elements, right? So this is the allyl group. Okay, so why it is more reactive? Because when it goes to ionization, ionization means this will goes to here. When it goes to ionization, the suddenly formed organic compound, the intermediate is CH2 double bond CH single bond CH2 positive, the allyl carbocation, which is very less stable, but which is stabilized through resonance. How? The positive charge in conjugation with a double bond. So this double bond goes to here. So CH2 plus CH double bond CH2. Okay. So nucleophile will attack this carbocation. Let me repeat again. When an allyl halide is there, which will suddenly goes to ionization due to the high stability of allyl carbocation through resonance, which is resonance stabilized through and nucleophile and facilitate the nucleophilic substitution reaction. Similarly, when we consider a benzyl halide, okay, when we consider a benzyl halide, this will also goes to ionization. Ionization. Ionization means the halide atom will readily remove when a nucleophile attack. So for me, a carbocation, a benzyl carbocation. As a result of that, it will goes to resonance. Okay, it will go to resonance. So the positive charge will comes here, double bond comes to between here. This will comes to here. Double bond comes to here. A positive charge comes here. This will comes here. So a positive charge comes here. This bond will comes here. So CH2 plus, right? So when a nucleophile attack this benzyl halide, the halide group will readily displaced from this moiety, this conjugated system, forming a carbocation, which is very stabilized through resonance, and as a result of that, the hybrid structure will become like this, and due to resonance, a positive charge. The electron density on the benzene ring decreases. So, which will facilitate the very immediate attack of a nucleophile, because nucleophile is an electron rich species, so which needs a positively charged center. So, due to resonance, the positive charge delocalized throughout the benzene ring, which will facilitate the very immediate nucleophilic substitution reaction. So, the, that is the reason why the high reactivity of allyl and benzyl halides over alkyl halides. One more thing to note, that in the case of alkyl halides, there is no resonance for alkyl group. Okay, there is no conjugation, right? There is no conjugation. That's the reason why alkyl halide is less reactive. The third application is basicity of ethylamine is greater than aniline. Aniline is arylamine. Why? So as you all know that the basicity of an amino group can be explained with the support of a Lewis base concept, because the lone pair is readily available for a protonation, right? Lone pair carried by the nitrogen atom is the crucial part of base to determine the basicity of amino group. So when we consider an ethylamine is nothing but CH3, CH2, ENH2. This is ethylamine. This lone pair is readily available for protonation. Okay, so proton to accept. So which is high basic. In addition to that, this alkyl group is having plus I effect, inductive effect, plus I effect. So which will increases the electron density on the nitrogen atom. As a result of that, the lone pair is readily available for protonation. So the basicity of ethylamine is very high. You can easily understand it, because the alkyl group is having plus I effect, which will donate electrons towards the functional group or the nitrogen carrying lone pair of electrons. When we consider aniline, due to plus R effect, this lone pair will comes here, will take part in the resonance. This will comes here. As a result of that, resonance will occur. NH2 plus minus, this will comes here. This negative charge will comes here. This will comes to this carbon atom. This will comes here, and this will goes to here. So you can see from this resonating structure that the lone pair on this nitrogen atom, or the lone pair carried by the nitrogen atom, the aniline, is not available for donation because this lone pair determine the basis because the lone pair is take part in the resonance due to Purcell effect. As a result of that, the basicity of aniline is very less compared to ethyl amine. Okay, why? Because the lone pair on the nitrogen atom is will take part in the resonance phenomenon. It is moving towards the ring. So as a result of that, lone pair is not available on the nitrogen atom. So its basicity is decreases. So when we compare with the methylamine, the basicity of aniline is very less. Okay. The fourth application to determine the acidity of carboxylic acid. We can use resonance effect to explain the acidity of carboxylic acid, how the carboxylic acid is acidic. So let's take the example of acetic acid, which is the famous acid, acetic acid, C double bond O H. So lone pair is there, lone pair is there. In aqueous solution, in water, in aqueous phase, this H plus ion will immediately released. So as a result of that, carboxylate anion, carboxylate anion is formed. Okay. So a negative charge in alternate position with a double bond. So resonance is possible. So this carboxylate anion is readily goes to resonance phenomena. This will comes to here, this will goes to here. So this carboxylate anion is resonance stabilized. Similarly, what will going to happen here? This will comes to here, this will goes to here. So carboxylic acid group also minus plus. So carboxylic acid also goes to resonance phenomena. So as a result, due to this plus charge, the release of H plus ion is become very easy. So the proton will immediately escape from this carboxylic group forming carboxylate anion. Why? Because carboxylate anion is very highly resonance stabilized. So it will get resonance stabilized. Hence, the release of H plus ion become very easy. As a result of that, there is a positive and negative charges happen. So charge separation occurs. Charge separation. Charge separation, remember this point, charge separation always decreases the stability of that group, that compound. Charge separation always decreases the resonance energy. When resonance energy decreases, stability of that particular compound decreases. So in order to gain stability, the carboxylic acid group immediately move towards carboxylate anion, which is resonance stabilized. Okay, this is the proper explanation to the acidity of carboxylic acid. Let me repeat again. The carboxylic acid group in aqueous solution releases H plus ion forming a carboxylate anion, which is resonance stabilized because of the conjugate bond, a double bond with a negative charge in alternating position. When we consider a carboxylic acid group, the lone pair present in the one of the oxygen atom, which is moved to this the single bond and alternative to the double bond is also moved to the another oxygen atom, forming a charge separation between carboxylic acid group. Charge separation always decreases the resonance energy, while decreasing resonance energy means the compound is less stable. As a result of that, forming a carboxylate anion is very become easy. Okay, so this is the explanation to the acidity of carboxylic acid. The fifth application is acidity of phenol and alcohol. Let's consider the example. Phenol is a benzene ring is carrying OH. Okay, when this is in aqueous solution, what will going to happen? O minus plus H plus. This is phenol. This is phenoxide. We will discuss the resonance stabilization of both these phenol and phenoxide. Let's consider first the phenol group. The lone pair is present over the oxygen will comes to here, and so this is plus R effect, right? Plus R. As a result of that, negative charge will occur here, and a double bond on this. The positive charge is here, and this will comes here. OH is having a positive charge. This will comes here. This will goes to here. OH positive charge. This will comes here. This will goes to here. So OH comes in here. Okay. So there is a charge separation. Charge separation. So resonance energy is very less. When we consider a phenoxide ion, this will comes here. This will goes to here. This will comes to here. This will goes to here. This will comes to here. This will goes to here. This will comes to here. This will again comes to this oxygen. So oxygen is carrying a negative charge. Okay. So there is no charge separation on phenoxide. Okay. So when we consider phenol in the resonating structure itself, which is evident that there is a charge separation. The positive charge is carried by the oxygen, which donate the OH group, the oxygen in the OH group, which donate the lone pair towards the ring due to plus R effect. And a negative charge is delocalized throughout the ring. So charge separation is there. So resonance energy is very less in the case of phenol. When we consider phenoxide, there's a lone pair as well as negative charge is there carried by the oxygen. So that negative charge is moved towards the benzene ring and which get delocalized throughout the structure, and the negative charge is delocalized. There is no charge separation. As a result of that, the stabilization of phenoxide ion is very high because which is more resonance stabilized than phenol. So we can say that phenoxide ion is more stable than phenol and which is more acidic than phenol. Phenoxide ion is more stable than phenol. Okay, and which is also more acidic in nature. So when we consider an alcohol, okay, when we consider an alcohol, so there is no space here. I will write it here. An alcohol, see, OH. What will happen? Due to plus I effect, the alkyl group will releases electrons towards this oxygen. Oxygen is already having lone pair of electrons. What is an acid? The tendency to remove H plus ion very easily. So, due to the electron releasing effect, the plus I effect of alkyl group will increases the electron density on the oxygen atom, which will hinder or backen the proton, the hydrogen atom, to immediate release from the alcohol group. So the release of H plus ion will become difficult due to the plus I effect. As a result of that, alcohol is less acidic than phenol. So alcohol is less acidic than phenol. Okay. So this is the way how we can explain the acidity of phenol and alcohol. In addition to that, we can also say that in the case of alcohol, see, when alkyl group OH is there in aqueous solution, RO minus plus H plus. In aqueous solution, RO minus is applied. This alkyl group is also increases the intensify the negative charge on this alkoxide group. This is known as alkoxide group, which destabilizes this group because charge increases, stability decreases. This is also the reason behind the less acidity of alcohol when compared with the phenol. Okay, so we can say that phenol is more acidic than alcohol due to the plus A effect on alcohol. The plus A effect of alkyl group on this alcohol, aliphatic group decreases the stability of alkoxide ion and also decreases the tendency to release H plus proton. Now we move on to the sixth application. Effect of resonance on dipole moment. So, how it affects the dipole moment? When we consider an example, this is an ethyl chloride. Okay, the dipole moment of this ethyl chloride is 2.05 mu d by dv. Okay, d by the unit of dipole moment. This is due to it is having minus a effect, so it will attract, it will pull the electrons towards itself, right? So when we consider a conjugated system like CH2 double bond CH, this is a vinyl chloride. Due to resonance, there is inductive effect is in this direction, minus a effect. Minus a effect is in this direction, but resonance that is plus R effect. Plus R effect or plus N effect, mesomeric effect, because a functional group is carrying a lone pair which is donated towards a conjugated system. Plus R effect in this direction. So both plus I and plus R in opposite, both plus I and plus R or plus M effect is in opposite direction. So as a result of that, the dipole moment will decreases to P. So this is the effect of resonance on dipole moment. So we are moving to discuss some examples using this application we have discussed here. So the first example, which is more stable? Which is more stable? There are two questions, 1 and 2. Which is more stable? This is an acetic acid, CH3C double bond OH, and this is the same with a charge separation. Which is more stable? Yeah, we can say that this is more stable. The first one is more stable because charge separation. Remember the point. Charge separation will decreases the resonance energy, thereby decreases the compound stability. So charge separation always decreases the stability of that compound. So acetic acid is more stable than the charge separator species. And which is more stable here? This is a CH2. CH2 is carried on an aryl group and a free radical on it. So a free radical and odd electron alternative to double bond. So resonance is possible here and resonance is possible here also. So number of resonance is 3. 3 bonds are there. Here 2 resonance possibilities are there, 2 bonds. So which is more stable? Absolutely, this one is more stable because the number of resonance structure is more in the case of the first one, because 3 pi bonds are there. Here only 2. So as the number of pi bonds increases, possibility of number of resonating structure also increases. When number of resonating structure increases, the stability of that compound is increases. Okay, so which is this one is more stable. So the next part of the question, which is more basic. So here, basicity of amines depends on the Lewis lone pair concept. When the lone pair is readily available for donation, is more basic. So due to plus I effect, the electrons, the alkyl group will releases electrons. As a result of that, the electron density on this nitrogen atom will increases. Lone pair is readily available for protonation. But here, this is an amide group, right? This lone pair is participating in resonance. So the lone pair is not readily available for protonation. As a result of that, basicity of this compound is very less. So basicity of ethyl amine is more than that of this case because resonance will decreases the possibility of using lone pair for basic purpose, basicity, which is more acidic here. This is a formic acid and this is acetic acid, which is more basic. Sodium, which is more acidic. Absolutely, this one is more acidic because the CH3 group is having plus I effect, will increases the density on the electron density on oxygen atom and which will hinder the release of H plus ion. Here, hydrogen is not having any plus I or minus I effect. As a result of that, the release of H plus ion in aqueous solution is become very easy. In addition to that, we can say that what will be the O minus and CH3 C double bond O minus. This CH3 group will intensify the negative charge on this carboxylate anion group, the oxygen atom, which will decreases the stability of this carboxylate anion. Whereas hydrogen does not have any plus A or minus A effect, so this is all get stabilized through resonance. So formic acid is more acidic than acetic acid. So these are the very few examples that we'll take from by using the application part. So you should familiarize with these applications for solving more questions. Okay, thank you.